Alright, this is for quiz 9. Webex didn't record. I just wanted to do this problem again for y'all real quick. We have a mass on an inclined plane. The angle was 30 degrees, 5 kilogram mass, and we're given a coefficient of static friction. And I say it's in static equilibrium and at rest, so there's no acceleration. What is the magnitude of the frictional force? Well, the reason I'm making this video is a lot of people jumped directly to, well, the frictional force is equal to mu times the normal force. And then they said, okay, that means I should draw a free body diagram that would make a parallel and perpendicular component of mg sine theta and mg cosine theta. And then we'd have a normal force, and they told us that friction was also acting. So if it wants to slide down the hill, friction would be acting up the hill. Always goes in the opposite direction of motion. So I want to know, what's the magnitude of that frictional force? The most common route and confusion I saw was people jumping to this formula, and this is wrong for this problem. Yes, that is the force, or the frictional force. It is the coefficient times the normal force, but that's going to give us the maximum frictional force that can occur. If we do this, we find out that we get a F max. Let's sum the forces real quick. If I look at the perpendicular direction, we have a normal force going up, mg cosine theta going down, and that equals the mass times the acceleration in the perpendicular. There is no acceleration, so we can cross that out, and we get the normal force is equal to mg cosine theta. Plugging that into our frictional formula will give us the maximum friction, not the friction that's actually holding it at rest. So I'm going to go ahead and crunch the number on this. We would get mu times mg cosine theta, and that comes out to be 25.5 newtons, a little less than that. That's the maximum, so that's not the answer we're looking for. What we need to do is see what is the magnitude of these two forces. There's only two going down the plane, the force of friction and the component of the weight going down the plane. If I sum those forces, call that the parallel direction, it's equal to the mass times the acceleration in the parallel direction. Once again, it's at static equilibrium, or acceleration is equal to 0. So we cross that out, and then we look at our forces. I have a frictional force going up. I have a minus mg sine theta going down. That all equals 0. So without doing any of this, which was actually only gave us the maximum friction, we can calculate the friction directly from mg sine theta. Because if they are balanced, if it is at static equilibrium, well, I guess if the forces are balanced, then they are in static equilibrium. We can say that. So these two things have to be equal to each other. We proved that by saying the acceleration was 0 and there's only two forces. So there we go. The frictional force is equal to mg sine theta, and that's 24.5 newtons. This is the answer we're looking for. That's the amount of friction keeping it from sliding down the incline. If we reduced that angle of the incline, say maybe theta is equal to 15 degrees, we would find out mg sine theta would actually even get smaller. So the amount of friction to hold it up on a smaller angle would be even less. And we can reduce that all the way down to a flat surface, right? If we have a mass on a flat surface, yes, there's absolutely a frictional force between here if you're applying another force, or if it's in motion. But if it's at rest, no friction is being exerted on either body. We have to push on one body in order to have the frictional force exert back. So let's say in this case the maximum frictional force was the 25.5, then we could apply forces all the way up until that point and it wouldn't move. and the resulting frictional force would always be equal but opposite to the applied force. Once we got larger than the magnitude of the force of friction, so if our applied force ended up being longer, then it'll break free and accelerate.